Welcome to the first lecture on homology theory. The original motivation for homology theory, specifically homology groups, was the observation that two shapes can be distinguished by examining their holes. That's mean, suppose you have a sphere, a two-dimensional sphere, and joining with a closed curve, or you can say cycle. Fine. Now suppose this topological space is X, and if you consider another topological space which is just union of three closed curve and they are touching at a single point. Suppose this topological space is Y, and we want to find either they are topologically same or different. Now note that if we consider the topological space X, then we have one dimensional hole and one two-dimensional hole, right? So this is my one dimensional hole, and if we consider the sphere, that will be a two-dimensional hole, right? Now if we consider the topological space Y, you can see that we have three one-dimensional holes and no two-dimensional hole, right? Therefore X has a two-dimensional hole, but Y does not have any two-dimensional hole. Therefore we can say that X and Y, they are not topologically same, that is, they are not homeomorphic. Now the question is, how do we define a hole? And the second question is, how can we distinguish two holes? Now look at the following figure. Suppose you have a torus. For a time being, assume that a one-dimensional hole means a closed curve which is not boundary of a region. Okay, that's mean if you choose this closed curve, then this will be a hole. Suppose call it C1. Okay, now choose another hole, this one. This is another one-dimensional hole, right? Now call it as C2. Now if you choose this closed curve, wrap in this side, now again this is also not a boundary of a region, right? So that's mean it is my C3. So this is also a hole. That's mean, so one dimensional holes mean roughly you can say that is not contractible. So you can see here, so this is a one dimensional hole, right? So this is not contractible. Okay, and this is also one dimensional hole, this is not contractible. Now suppose you have a disk, that closed disk, and if we take this boundary, now this is not a hole, right? Because this is a boundary of a region. So this region, so this curve can be contractible within the region, right? Therefore this is not a hole. But if you take, this is my disk, now if you take a circle only S1 and we consider the closed curve this, then it is not a boundary of a region. That's mean within the topological space S1, this closed curve is not contractible. Therefore it is a hole. Now if we look at the torus again, then C1, C2 and C3 are three holes, and later we shall see that the holes C1 and C2 are equivalent in some sense, but both of them are not equivalent to C3. We shall see this later. Fine. Now the question is, in this torus, are they only holes? Now we shall answer of this question. Now consider the torus again. Fine. Now we choose one hole in this way. So we start with this point, we go in this way, this, and we come via the back side. Okay, this one, right? Now this is another hole. Why this is an hole? Because this is not a boundary of a region, and also it is not contractible, right? So therefore call it as C4. Now the question is, what is the relation between C1, C2 or C3 with C4? Is there any relation between them or not? Okay. Now there is another question. Consider the torus again. Now what will happen if we wrap twice? That's mean we start anti-clockwise, we wrap again, and we join with that point again, right? Now again this is a hole because it satisfies our definition, so it is not contractible, or in other words it is not a boundary of a region. Fine. Now call it as C5. So we start with in this anti-clockwise. Now what will happen if we say take torus and we start anti-clockwise? Say this and this, and again we start this, right? Now call it C6. Now the question is that C5 and C6 are same or different. So we will see this later. Now for a time being I shall state that C5 and C6 are different. In our course we shall not use the term hole. Okay, instead of hole we shall write homology classes. That's mean, so in our course hole, the term hole will be replaced by homology class. And we prove that maybe on tomorrow the collection of n dimensional holes that is homology classes forms a group in some sense, and they are called the nth homology groups of the topological space. Let's see one example. So consider the torus again and with the holes C1, C2 and C3, right? I have already stated that the hole C1 is same as, that is equivalent to the hole C2, right? In other words, in the homology classes we can say that the homology class of C1 is same as the homology class of C2, right? And I have also stated that C1 and C2 are not equivalent to C3, right? That means in this sense we shall say that the homology class of C1 is not same as the homology class of C3, right? Now since we shall see later that the collection of all these homology classes forms a group, so in this torus example we shall see that the one dimensional homology group of torus will be Z cross Z, and it will be generated by this C1 and the homology class of C3. Okay, so this will be my group. In other words, so what was my C4? So C4 was this one, right? So we start with here, we wrapped this and we go via the back side, right? That's mean in this case we shall see that that C4 is actually will be my C1, that group composition with C3. That's mean if we wrap one this side and then with this side, then we will get actually C4. And for the C5, we shall see later that C5 will be my C3 with group composition with C3. That's mean if we go 2 times on C3, that will be equivalent to C5, and the C6, which is in the reverse direction, will be my C3 inverse group composition with C3 inverse. So don't worry about this because we shall see this later. So we shall see later that the first homology group, that is one dimensional homology group of the torus, will be Z cross Z, and which is generated by the cycles C1 and C3. Fine. Actually, homology group is a bridge between topology and algebra. Though homology groups are originally defined in algebraic topology, but similar constructions are available in a wide variety of other contexts as well, such as abstract algebra, groups, Lie groups, Galois theory, and algebraic geometry. So that's mean homology theory, you can say, is very useful to classify manifolds with respect to some topological invariant. Now for a topological space, say X, there are many ways to compute the homology groups. In each case, we have different names. So one is simplicial homology, another term is singular homology, and another term is cellular homology. Okay, so the singular homology can be obtained for any topological space. Okay. Now the simplicial homology of a topological space can be obtained if the topological space has a simplicial complex structure or a delta complex structure. Okay, but in this course I shall use this term, that is the delta complex structure, and there is another one, that cellular homology. Now the cellular homology of a topological space can be obtained if the topological space has a CW complex structure. Note that if you have a topological space, then you can always compute the singular homology. But the computation of singular homology is a difficult job because it involves a lots of maps. Therefore, the singular homology mainly serves the theoretical purpose. But for the practical purpose, that is for the computational, we always use the simplicial homology, because if you have a topological space which has a delta complex structure or simplicial complex structure, then you can always compute the simplicial homology, right? Therefore, for practical purpose, we use the simplicial homology. Also, the cellular homology serves the practical purpose. That's mean if you have a topological space which has a CW complex structure, then you can compute the cellular homology. And there is another note that if you have a simplicial complex, then it is also a CW complex as well. But the converse is not true. That's mean you may have a CW complex which is not a simplicial complex. Fine. But for a topological space, if you can compute singular homology or simplicial homology or cellular homology, then they will be identical. That's mean they will be same. So here I write, for a topological space X, the singular homology is same as the simplicial homology. Obviously, if exists, we don't know it will exist or not, right? Because it will exist if it has a delta complex structure. And also the singular homology is same as cellular homology, again if it exists, right? Therefore, we can have a outline of this introduction. That's mean if you have a topological space X, then we can compute the singular homology, we can compute the simplicial homology, and we can compute the cellular homology. So for a topological space, we can compute the singular homology, it is directly, right? We can compute the simplicial homology via delta complex structure or simplicial complex structure, but here in this course I shall use the delta complex structure, right? And for a topological space, you can compute the cellular homology as well via CW complex structure. This is just an introduction. So we shall know all the terms and we shall see all the results in the upcoming lectures. So now we start with the simplicial homology. Let's start with basic definitions. So first of all we have N Simplex. So let V0, V1 up to Vn be n plus 1 points in some Rm. So we can write here for some m bigger equal to n. Now this n plus 1 points has some properties. So we can write such that the points V0, V1 up to Vn do not lie in a hyperplane of dimension less than n. Or equivalently, or we can write equivalently, we can say that the n vectors V1 minus V0, V2 minus V0 up to Vn minus V0 are linearly independent in Rn. For an example, if you have 3 points, then these 3 points should be in a plane. So should be in a plane, that is in R2, but definitely not in R. Okay. Now if you have 4 points, then these 4 points should be in R3. Should be in R3 but not in R2. That's mean, suppose you have 3 points, then this is not allowed. So these 3 points should not be in a line, but we should have this kind of 3 points. That's mean this should be in a plane, right? Now if you have 4 points, then this type of 4 points is not allowed. So this should not be in a plane. So we should have, say, these 3 points, right? And another point should be somewhere in the upside. So you can think in this way. Okay, fine. Now we will define N simplex in terms of this n plus 1 vertices. So now the smallest convex set in Rm containing these n plus 1 points is called an N simplex. And if it is generated by V0, V1 up to Vn, then it is denoted by this symbol. So we will write that V0, V1 up to Vn in a third bracket. Okay. Now the points that V0, V1 up to Vn are called the vertices of this N simplex. So here we can write the points V0, V1 up to Vn are called the vertices of the N simplex, this one. Okay, that's mean you can say that an N simplex has exactly n plus 1 vertices. Okay, that's mean the spanning set is called the vertices of the N simplex. So for an example, what will be a zero simplex? So a zero simplex will be just a point, right? Now what will be a one simplex? So one simplex is a convex set containing 2 points, right? That's mean it is a line segment. Now what is my 2 simplex? So 2 simplex is generated by 3 points, right? Those 3 points do not lie in a line. So it is the smallest convex set containing this type of 3 points, right? So it is this set, right? So a 2 simplex is just a triangle. And what will be a 3 simplex? So it will be a convex set containing 4 points which do not lie in a plane, right? So we have 3 points, these which lie in a plane, and then we have another point, say this one, which do not lie in this plane. Okay, so that's mean we have a triangle, this, and then this is a point which is in the different plane. Okay, so we will join with this one. Fine. So we get a tetrahedron. See here, there is no intersection. Okay, so this is a line, there is no intersection. You can think that there is a triangle in a plane and then you are taking a cone from a point which is do not lie in that plane. Fine. So this is a 3 simplex. So 3 simplex is a tetrahedron. Now for a N simplex, we can define a face of the N simplex. So what is a face of a N simplex? So let we have an N simplex. So it is generated by n plus 1 vertices. Now if we delete exactly one vertex, then the n minus 1 simplex spanned by the remaining n vertices is called a face of the simplex. That's mean we can write for 0 less than equal to I less than equal to n, the n minus 1 simplex, this one, say v0 up to vi minus 1, vi plus 1, then vn. That's mean the vertex vi is deleted. Okay, which is spanned by the vertices v0, v1, vi minus 1, vi plus 1, because vi is deleted, up to vn. right? Now span by this is called a phase of the simplex, this one. Right? That's mean if we have an n simplex, then it has exactly n plus 1 faces. That's mean if we remove each n plus 1 vertices, then we get a n minus 1 simplex, and that is called a phase of that n minus n simplex, right? Now that n minus 1 simplex is also denoted by this symbol, say v0, v1 up to vi minus 1, then vi cap, then vi plus 1 up to vn. Okay, so where vi cap means the vertex vi is deleted. Okay, next we talk about the order. That's mean whenever we talk about n simplex, that's mean we should maintain one order of its vertices. So here is the definition, or we can say the observation. So here an n simplex v0, v1 up to vn means the n simplex with ordering of its vertices. Okay, so here we always assume that the order is v0 less than v1 less than dot 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 less than vn, right? So in other words, so if you have a simplex v0, v1 up to vn, or we can write here v3 as well, so v3 and then up to vn, this simplex is not same as the simplex v1, v0 and then v3 up to vn. That's mean if we change the order, that is first and second vertices, then we will get a different simplex. Okay, that's mean whenever we talk about the simplex, then we talk about the order of the vertices. So what do you mean by not equal? So in the sense of orientation. Okay, so we shall see later that this is exactly minus of v1, v0, v3 is vn. Okay, anyway, we shall see this later, right? Don't worry about that. So for a time being, just assume that whenever you have a n simplex, then if we write as v0, v1 up to vn, then you should remember that we have an ordering, and this ordering is this way, that is v1 less than, sorry, v0 less than v1 less than, and it is going up to vn. Fine. And also if we talk about a phase of a simplex, Okay, we always maintain the ordering of the larger simplex. That's mean we assume the order of the vertices of the larger simplex. Okay, so next we have boundary and interior. So boundary of interior of a simplex. So first of all, let delta n be an N simplex. So when we do not need the vertices, then we sometimes denote the N simplex by delta n. But when we need the vertices, then we denote the N simplex by that symbol, that is V0, V1 up to Vn in the third bracket. Okay. So to define the boundary and interior, we first choose delta n be an N simplex. Okay. Then the union of all the faces of delta n is called the boundary of delta n. Okay, and it is denoted by that is boundary of delta n. Okay, and from the delta n, if we remove the boundary, then we have a open simplex. That open simplex is called the interior of delta n. So the open simplex is, so delta n minus boundary of delta n is called the interior of the simplex delta n. Fine. That's mean suppose you have a triangle with the region this. Okay. Okay, then this is my delta n, actually here n equal to 2. Now this red colored boundary is called boundary of delta n, and if we remove that red colored boundary, so the interior part, the inside green region is called the interior. Okay, so here n equal to 2. Fine. Now we are ready to define delta complex. So let X be a topological space a delta complex structure on X is a collection of maps we can write this map as sigma upper script n and lower script alpha from delta n to x. Okay, and we call this collection as script x. That's mean this is a collection of all the sigma upper script n lower script alpha, which is a map from some delta n, that is from some n simplex to x, where alpha is some index set, we don't know what is it, obviously it is a finite index set, and n equal to 0, 1 up to, it may be up to infinite. Okay, and this collection should satisfy some property. So we write here such that, so this is the first condition the collection should satisfy. First of all, we have a map sigma from delta n to x, right? Now if we take the restriction of sigma n in the interior of delta n, then the restricted map should be injective. That is, the restriction sigma n alpha in the interior of delta n from delta n interior to x is injective, and it has another extra property that each of x belongs to x is in, or you can say lies in, exactly one of the image of this sigma n alpha delta n interior. Okay, that is, you can say that the topological space X is equal to disjoint union of over all the alpha and n and the image of the interiors. This second condition actually says, suppose if we have this topological space X, okay, and if we have one delta in interior, and if the image is say sigma n alpha 1, this one, and if we have another interior say delta m interior, and if it maps is say sigma m and alpha 2, then the image should be disjoint from the previous one. That's mean this case will not happen. So this should not be the case. Okay, fine. So this is one condition, and the next property is this one. So each restriction of sigma n alpha to a face of delta n is also in that collection. That's mean is one of the maps say sigma n minus 1 beta from delta n minus 1 to x in the collection script x. Okay, in other words, it says suppose sigma n alpha belongs to that collection script X. That's mean sigma n alpha is a map from delta n to X, right? Now choose delta n minus 1 a phase of delta n. Okay, so sigma n is a map from delta n to X, and we choose one phase of delta n. Then if we take the restriction map, that's mean sigma n alpha restricted over delta n minus 1. Then it will be a map from delta n to X, right? Now this condition actually says this restriction map says sigma alpha n delta n minus 1 also in that collection. Fine, and we will call it is, since it is a map from delta n minus 1 to X, so we call it is by some sigma n minus 1 and say different indices beta. Fine. Okay, so this is the second condition, and the third condition is topological. That means we will give the topology on the delta complex. Now third condition says a set A subset of X is open if and only if we have that sigma n alpha, the inverse of A, is open in delta n for each sigma n alpha. Fine. That's mean whenever we have an open set A in the topological space X, then its inverse image by the each of the map should be open in that simplex. Okay, that's mean we can give a topology on the delta complex, and with respect to that topology we can easily check that our map say delta n alpha restricted over that interior. Okay, so we have seen that it is a map from delta n interior to X, right? And this map is injective. Now if we restrict my codomain as well, say it is sigma alpha n, this one. Now this is injective as well as it is surjective, and by using the topology which has been mentioned in the item 3, this one, these maps are actually homeomorphism. That's mean, and we have also seen that X equal to disjoint union of sigma alpha n that interior of delta n, right? That's mean if we know the images of the interiors, then we shall know the delta complex structure on the topological space X. Fine. Okay, now we shall see one example to understand this one. So here is one example. So first of all, take my X is torus. So what is a torus? That's mean we have a rectangle, right? Now if we identify this with this edge with this edge, right, then we will get a cylinder, right? Now again, if we identify this with this, that's mean we will identify this with this, right? Then we will get a torus. Fine. Now this is my topological space X, or this. Now we shall give one delta complex structure on this topological space, that is on torus. So first of all, we choose this rectangle, this one. So we need to embed the interior of triangles, right? That is the reason we divide this into two parts, so that it looks like a triangle, right? So union of triangles. So now call, this is my U, this is my L. Fine. See, we identified this edge with this edge, right? That's mean they are actually same edge. So we will name it by A, and this is A. And similarly, this edge and this edge are same, right? Because they are identified. Therefore, we call it by B. So B is one edge, right? And we have another edge, this one, that interior one. So we call it by C, right? Now we have three edges actually. So you can say image of the edges. Fine. Now note that, so these are the vertices. Now we actually show that these are actually single vertex, not the different one. Why? First of all, note that here, suppose this is my V0, V1, V2 and V3. Okay. Now since we identify, so first remove that one so that you can understand. Now first, since we identify this with this, that's mean V0 is identified with V2, right? And V1 is identified with V3. So this is my V1, right? Since we identified this edge with this edge. Okay. Now again we identified these edges with these edges. That's mean this V0 and V1 are identified, and this V0 and V1 are identified, right? Therefore, this is also V0 and this is also V0. Therefore, we have actually one vertex. So call this vertex as V. So this is same as V, right? That's mean we can write X, the topological space which is torus, is union of U, union L, union A, union B, union C, union the vertex V, right? Now note that A, B, C are not edges, and U and L are not triangles, right? It can be a image of a triangle, but it is not a triangle. You can check that. If you look at U, then all of these three vertices are identified, right? So it is not a triangle. Similarly, L is not a triangle. Similarly, B is not an edge, right? It is just a what? Circle, because we have a line segment and then both in point are same. That's when B is actually a circle here. Fine. But we can talk about B as a image of an edge or image of an one simplex. So here we can note that U and L are not two simplices, right? A, B, C are not one simplices. But we can talk about U and L are image of two simplices, right? And we can talk about ABC are image of one simplices. Note that if we take a map, say this one to A. What is A? A is a circle, right? Now if say this is my x0, say this is my x1. Now if under this map say sigma 1, say alpha, then if sigma 1 alpha x0 equal to this V and sigma alpha 1 x1 equal to V, okay, and in the interior, if the map is injective, then we can get this image, right? That's mean we can define a delta complex structure here. So how we will define a delta complex structure? We will just define U, okay, as a image of a map sigma 2 1, say it is sigma again 2, say 2, it is sigma 1, say 3, say it is sigma 1, say 4, say it is sigma 1 5, and say it is sigma 1, sorry, it is from 0 simplex to 6. Okay, now this way we can define a delta complex structure on X. So we will write, let sigma 1 2, right, sigma 1 2 is a map from delta 2 to X, or you can write here 2 to U subset of X. Fine, is a map from delta 2 to L, again subset of X, delta 3 1, delta 1 to A, right, we have choose it as A subset of X, to B subset of X, C subset of X, and this is 0 6 from delta 0 to the vertex V, again it is subset of X. So we take this collection sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, and sigma 6. We need few more restrictions. First of all, we can check that sigma 6 not if you take the interior, right, so delta 0 interior is delta 0 itself and it is V, this is also a point and this is also a point, right. So now this map is already is injective, right, and since both side we have point only, so you can say it is a surjective as well, so we can say it is a homeomorphism. Fine, since both side we have point, so we can define such a homeomorphism. Now what we can do, now define in this way that sigma 3 1, okay, now if we take the restriction of delta 1 interior from delta 1 interior to A minus V, that's mean we have the circle A and we remove the point V. Fine, then we can define, so this is also a open one simplex, this is also a open one simplex, right, so we can define as a homeomorphism. Right. Also, if we take the map sigma 1 4 and if we restrict it on delta 1 interior to B minus V, then this is also a homeomorphism. That means we can choose a homeomorphism since both are the open line segment, that is open simplices, right? Now similarly, if we have sigma 1 5 restricted over delta 1 naught, then it is a map from delta 1 naught to C minus V, and this is also a homeomorphism, right? So both are homeomorphisms. Now again, if we take the map sigma 1 2 and take the restriction on delta 2 naught, then it will be a map from delta 2 naught to U minus A minus B minus C, right? Again, both sides we have open two simplices, therefore we can define a homeomorphism. And last of all, if we have sigma 2 2, then if we restrict it over delta 2 naught, then again we have a map from delta 2 naught to L minus A minus B minus C. And similarly here, this is one open two simplices and this is also a open two simplices, so we can define homeomorphism, right? So these are homeomorphisms. Now if we define these homeomorphisms, then you can check that this collection of maps satisfies all of those properties, this, right? For an example, suppose we want to check the first property. Now what it says? It says the restriction map is injective. Now we have already taken it is homeomorphism, so it is injective, right? Now the second condition is for each x, right, it lies in exactly one of this one. Now you can check that if this is my topological space X, right? Now if we choose any one point, suppose if we choose a point, say this one, then it is interior of U. If it is the point is this, then it is interior of L. If the point is here, then it will be the interior of C. If the point is here, then it will be interior of A. If it is here, then it will be interior of B. And if it is the vertex this, then it is interior of the vertex B. Therefore the first condition satisfies, right? Now what about the second? Now this is the second. Now it says if you have a map, that is if you take a collection from script X and if you take the restriction, then the restriction map will be also will be in that collection as well, right? Now here you can check that suppose we have a map this delta 2, say sigma 2, right? Now it is a map from delta 2 to L. Now if you take the restriction, so it has three faces. Now according to choices of faces, you will get the map sigma 3 1 or sigma 4 1 or sigma 5 1, right? Therefore the second condition also satisfied. And the third condition, now it says a subset of X is open if and only if the inverse is open for all the map sigma. Now we have already taken it is homeomorphism in the interior, therefore the last condition also satisfied. Therefore this script X gives a delta complex structure on the topological space X, right? So in the next lecture I shall give one more examples and then I shall use the delta complex to compute the simplicial homology. So we stop here, see you in the next lecture.